Someone open the door.
Wait, is your campus working okay?
It was very slow this morning, and I
Right,
haven't
no,
accessed it yet. Yeah,
very slow.
yeah,
And now it won't even load, so I was just wondering.
yeah. Dave sent a email
Okay.
yesterday about something about Canvas not loading or something.
Oh, this morning?
Yesterday.
Yeah, that was like some error messages people were
Oh,
getting,
I don't know.
but that was supposed to be fixed. So, all right, just checking things. Sorry.
Nick's too, but it's Nick, so you never.
Yeah.
All right, so valence bond theory, which is what I'm going to teach molecular orbital theory for you guys, okay? So whoever was in the bathroom. So valence bond theory, which is the hybridization, that is helpful to understand how strong the bonds are, how many bonds you can actually form, how rigid the bonds are. Remember, when you rotate a double bond, that pi bond can break. So like, how rigid is that bond? That's helpful to understand. But there are certain things that it can't predict, like why does liquid oxygen get attracted to a magnetic field. Okay, so the way that we form the bonds in oxygen does not explain why that happens. Okay, we know that paramagnetism requires unpaired electrons in the orbitals, right? But if you try to do the bond for oxygen, there doesn't seem to be any unpaired electrons. Everything is paired. So how come that it's still attracted to a magnet? Okay, so that means our orbitals must be wrong because it's an observable phenomenon. Okay, so in valence bond theory, also the electrons are localized in the atoms of the molecule. Like each atom will have its own electrons. They're kind of localized. Like, okay, these electrons belong to this atom, these electrons belong to this atom, etc. But it doesn't account for the real delocalization that we see, which is electrons in pi bonds can actually spread out beyond the atoms where they come from. Okay, so imagine that oxygen has a p orbital that is participating in another p orbital's pi bond, like a carbon's p orbital, unhybridized. Those electrons don't necessarily stick around with those particular atoms. They kind of get delocalized in the entire molecule. So valence bond theory does not account for that, because valence bond theory says a pi orbital or a p orbital will overlap to form a pi bond, and this bond will be where the electrons are. But in reality, like let's say this is oxygen, this is carbon, it's connected to something else, whatever. Okay, there's a bond here, formaldehyde basically, right? These electrons don't just stick around here, they actually spread out in the entire molecule. A lot of them around oxygen because oxygen is more electronegative, but the probability density of them is kind of like everywhere. So it doesn't account for delocalization. Okay? Also, something like this, the structures that we have been seeing, this is called a benzene ring. Okay, we know that these double bonds are not necessarily just here, or just here. In fact, you can just draw this hexagon like this and say that the entire, all of the bonds have some double bond character by showing it like that. And this is often how benzene rings are drawn. So if valence bond theory says that this carbon is sp2, this carbon is sp2, and those electrons are localized over there, there's nothing to explain why this happens. Why does resonance exist? Why can electrons spread out like that? None of the theories that we have can account for that. Okay, so molecular orbital theory, that's where this comes in. Now, it's a lot to read, but we're not going to read everything. I'll explain it. Okay, molecular orbital theory, we take Schrodinger's equation for wave functions and we apply it to the entire molecule instead of individually calculating orbitals for atoms and then using them to bond. Instead of doing that, we apply the variables to the entire molecule. Okay? But you can't actually solve it for the molecule. What you can do is imagine an answer, like what we call, like if you have a question, you figure out what the answer is first and then you work your way back to figure out what the question is. That's kind of how you do this. Okay, So we call that a trial function. We say, okay, maybe the orbitals look like this. If that is the case, how is the bonding? Okay, so those are called trial functions. You kind of propose a theory first, like a hypothesis, and then you see if the math matches your hypothesis. Okay, so the trial function, you test the trial by substituting it into Schrodinger's equation, and then you try to solve it to see if the energy works out. Okay, a computer program does this because Schrodinger's equation takes a long time to solve, and also it's incredibly complicated for a molecule. Okay, you're never going to find a hypothesis or a trial function that is better than what's actually found in nature. You're not going to be like, oh, look at my answer, it's so much better. Why doesn't the molecule bond this way? You're never going to find some answer that works better than what already exists, okay? And we are not necessarily exactly getting what exists either, because you can't actually measure the energetics of each orbital. You are trying to get as close as possible so that the math works out, so that the bonding in the molecule matches what you know about it, okay? Now, here's the main thing. In molecular orbital theory, the electrons and their probability densities belong to the entire molecule. Okay? So in valence bond theory, when I say carbon, the central carbons, 2s and 2p, hybridize and make 4sp3 hybridized orbitals. Those orbitals belong to only carbon. Okay, but in molecular orbital theory, you're putting every single valence orbital into a bucket. You're mixing them up, and you are basically dispersing the probability density of the entire molecule. Okay, that's kind of the only way to visualize it. So you dump everything together, you mix it up, and then you kind of distribute it based on how electronegative the element is. Okay, now, or how likely it is to share and bond. So what we are going to look at is only one way to get a trial function, and that is called LCAO, or linear combination of atomic orbitals. Okay, one, you will never be asked what it is, so you don't have to like memorize any of this. I'm introducing the logic behind what you are about to see. Okay, so linear combination of atomic orbitals is literally exactly what it sounds like. You are combining atomic orbitals linearly to form a molecular orbital. Okay, linear combination of atomic orbitals, molecular orbitals, are weighted linear sums of the valence atomic orbitals of the atoms in the molecule. Here's what it actually means. You take all the valence orbitals, or the orbitals that the valence electrons existed, and you dump them into the bucket. You mix it up. Then you take the probability densities and you give more weight to the more lower energy orbitals, and you give less weight to the higher energy orbitals. Okay? Now this might not make sense until you see a molecular orbital diagram. Linear combination of atomic orbitals looks like hybridization, but it is not, because hybridization is only for individual atoms. This is for the entire molecule. So you can think of it as hybridization of the entire molecule. Instead of carbons 2s and 2p that's hybridizing, you're hybridizing every single atom's valence orbitals. Okay? You're mixing everything up to come up with molecular orbitals that are lower and more stable in energy. Okay? Now, just describe that. This is very important actually, because the orbitals now belong to the entire molecule. The electrons in those orbitals also belong to the entire molecule, which is why delocalization works. Okay? Delocalization is not a complicated word. Local means in one place, delocal means like not in one place. It's spread into many places. Not localized, delocalized. Okay? Now, remember wave behavior in chapter 6? This is how orbitals interact. When you have two orbitals interacting with each other through constructive interference, we say you form a bonding molecular orbital. Okay? And those are the ones that are involved in making sigma and pi bonds. It's the same terminology, it's the same symbols as hybridization, but it's not the same kind of bond. A pi bond is not a double bond here, okay? It's not the second bond of a double bond. It's just a type of bond, okay? This is why it gets confusing. Okay, then if your two orbitals interact destructively, you get anti-bonding molecular orbitals, but anti-bonding does not mean that they don't form bonds. It means they're just higher in energy. Okay? The terminology does not lend itself into easy understanding. So higher energy orbitals are called anti-bonding orbitals and they are labeled sigma star and pi star. So two orbitals interact, you're going to get a bonding orbital and you're going to get an anti-bonding orbital because when orbitals interact, they will interact both constructively and destructively. Because remember, it's a wave. Parts of the wave will be constructive, parts of the wave will be destructive. Okay? They're not exactly aligned. So here is what happens. This is an extremely cartoonish version, but it's kind of helpful to understand. If you have two s orbitals constructively interfere with each other, you get a larger molecular orbital, and that is called bonding orbitals because it's lower in energy than both of these individual 1s orbitals. Okay? These individual 1s orbitals are higher in energy. When they interact with each other, you get a bonding orbital that is lower in energy than either of those. Then, if they destructively interfere with each other, you get an anti-bonding orbital. And in anti-bonding orbitals, you have an area where there is no electron density.
We are aware that Canvas is down. It's not just here, it appears to be nationally. We will let you know when it's back up. Thank you.
Okay, so here is the anti-bonding interaction. Some of the wave is cancelled out. Remember, anti-bonding or destructive interference means parts of the wave gets cancelled out. So the internuclear region between the two nuclei, this region, there is no electron density there. That's the most stable place for electrons to be, but it can't be in an anti-bonding orbital. And because of that, it's higher in energy. Okay, so you are never going to be tested on this diagram. I'm trying to build your understanding, so when I show you a molecular orbital diagram, you understand what's going on. Okay, constructive interference lowers energy, destructive interference increases energy, and in the most stable place in the orbital or most stable place in a bond, there can't be any electrons. Okay, that makes electrons present here and here have higher energy. Okay, and these two things are not in phase, which is why this is blue and this is red. They're not in phase with each other. They're kind of like out of phase with each other. Okay, out of phase waves. Okay, like one could be going like this and the other could be like, I don't know how to do it with my hand, maybe like that. Okay, out of phase with each other. All right, this is a molecular orbital diagram. You might have to interpret it. So here's how you interpret it. One side is one atom participating in the bonding. Other side is the other atom participating in the bonding. So you are making this molecule, H2, diatomic hydrogen. If the 1s orbital of each hydrogen atom constructively interferes, you will end up forming a bonding orbital that is lower in energy than both atomic orbitals. So these are molecular orbitals and these are atomic orbitals. Okay? So they will constructively interfere and form a bonding orbital. They will destructively interfere and form an anti-bonding orbital. Okay? It just means higher in energy, not that they're not going to have electrons in there. Each hydrogen atom has one valence electron. So when you fill a molecular orbital diagram, you fill it the same way you would fill any electron configuration. You start with the lowest energy first, and then you work your way up. So one electron from this hydrogen atom fills it, but you can't put the next electron here. You have to fill this before you move on to the next orbital. So this electron goes here, this electron goes here. You have a sigma bond formed in the bonding orbital. Okay? We know diatomic hydrogen exists. Diatomic hydrogen has two electrons in a bonding orbital that is a molecular orbital and no electrons in the anti-bonding orbital. Number one, you never have to draw it, you just have to interpret it. Number two, you will never have to fill it, you just have to interpret it. Okay, that's it. Now we know that it exists, but we don't know why it's stable. We know it's stable, but we don't know why it's stable. So there's a way to calculate stability. We're getting to that, okay? Here is a possible molecule, diatomic helium, okay? We're trying to figure out if this is possible or not possible, okay? Now, helium has two electrons in its 1s orbital. This is helium's 1s2 orbital. This is helium's 1s2. These are atomic orbitals. They will interact and form one bonding and one anti-bonding orbital. Okay, question, Tosca.
Will both of the arrows on the left go to the bonding one, or will it be the
No, it's one each. One here, and one here, one here. Okay? So if you don't know how many boxes will be in the middle, it's really easy to find out. If they ask you to interpret the correct diagram, you would be looking at the number of boxes that equal the atomic orbitals. Okay? The number of molecular orbitals that form are equal to the number of atomic orbitals that go in the puzzle. Okay? So you would fill it just like you would fill using Aufbau. One electron here, one electron here, you form one bond here, and then another electron there, and another electron there, and you expect that to be the way He2 exists. Okay? Now we have to figure out if it does exist. If it does exist, is it stable or not stable? The way you figure out if it's stable or not stable is by doing something called bond order. It's very, very easy to do. This you might have to do given a molecular orbital diagram. But since you never need to draw one, you just need to interpret one, this is something super easy to do. Okay? So bond order is basically how many electrons are in bonding orbitals minus how many electrons are in anti-bonding orbitals divided by 2. If you get a positive bond order, that means you have more electrons in the stable orbitals than the unstable orbitals, and therefore you will have the existence of that molecule. It will be more stable. Okay? A positive bond order will indicate more electrons in bonding molecular orbitals than anti-bonding molecular orbitals, and the electrons in the bonding molecular orbitals will have lower energy than they had in the atomic orbitals. Okay? Higher the bond order, you want this number to be big. Stronger the bond. Okay? A negative or zero bond order will mean that this molecule does not exist. So let's go back to hydrogen. Calculate bond order for this. Bond order equals the number of electrons in the bonding plus the number of electrons in anti-bonding divided by 2, which would give it a bond order of 1. It's positive, it exists, and it's stable. Okay? What about this one? What's the bond order? 0, right? There's 2 here plus 2 there divided by 2. Who's that? Wait, did I? I'm sorry, it's my bad. I apologize. I did the same thing in the other one, I think. I keep putting plus. There. Had to make it straight in my head. Zero bond order. Does this molecule exist or no?
No.
No. So if you get a zero bond order, it can't exist. If you get a negative bond order, it can't exist. Negative bond order would be if you have more molecules in the antibonding orbital, it's just not stable, so it can't exist. Okay? So what about this one? What is the bond order? He2 with a plus. 1/2. Is it positive 1/2 or negative 1/2? Does it exist? It exists. Okay. So valence bond theory, Lewis theory can't account for the existence of a He2 plus ion, which is also covalently bonded. Okay. You have helium's valence shells combining to form one bonding and one antibonding. Two electrons in the bonding, one electron in the antibonding makes this stable. Yeah, not greatly stable, but it exists enough to be. It's less stable than hydrogen because it has a positive bond order. One more stable than something that doesn't exist, right?
So the closer it gets to zero, the less stable.
Yes. Mhm. So you can pretty much figure out if any of your second period diatomics can exist. So we don't go beyond second period for molecular orbital theory. Okay? Anything in the second period, like lithium, beryllium, you can calculate if those things exist, even though lithium is a metal. Could it form a covalent bond with something? Could it form a covalent bond with another lithium atom? Is that possible? That is something you can interpret based on molecular orbital theory. Okay? So skipping this because we're not drawing. I used to have you guys draw, but we're not doing it. Let's just look. Li2 molecule, atomic orbitals will mix the 2s orbital. One bonding, one antibonding. Can diatomic lithium exist? What's its bond order? One. Definitely exists. Okay? What about diatomic beryllium? Cannot. Zero, right? Okay. Then here is how p orbitals will interact. We just looked at s. Yeah.
Are they always diatomic?
No, we're just seeing, like, we're making up molecules to see if they'll work out. If what we see in the universe is possible. Okay? So here are p orbitals. This is interaction of p orbitals. This is what a radial distribution function looks like for a p orbital. Okay? Look, if p orbitals directly approach each other, you'll have constructive interference. If the part of the p orbital that is, so this is like positive, that is like negative, okay? If this and another positive end interact with each other, you're going to get this like candy shape, which is a bonding orbital, where there's a huge electron density between the two nuclei. Anything between two nuclei is stable, right? So that's what you should spot. The little dots, those are your nuclei, okay? If a side that's like this interacts with a side that is positive, you have out of phase interaction. So you form an anti-bonding orbital where the distribution of electrons between the two nuclei, there's a huge node here and only a small distribution, okay? Most of the electrons are on either side of the nuclei. Internuclear space is the most lower energy, lower potential energy, okay? And then here is how they would interact side to side, parallel, pi bond formation, right? If the in phase interact with in phase, you would have this where they overlap, and you have a bonding orbital above and below the two nuclei, very stable, okay? Here, destructive interference, there's a node in the middle. No electrons can be present here, and electrons can only be present almost very similar to the original p orbitals. Okay? Again, you never have to draw or interpret this. I'm just showing you this, how they interact to form the bonding and antibonding orbitals. Okay? So they can interact head to head or they can interact parallel. Those are the two ways that they can interfere with each other. All right, now this is in your textbook. This you need to know. Not to draw, but to explain. Okay? These are all second period. This is the p block in the second period. Okay, Bc and OF and E. Boron, carbon, nitrogen, oxygen, fluorine, neon. But diatomic versions of everything. Okay? Here is what you should pay attention to. The relative order of molecular orbitals is for linear combination of atomic orbitals. Molecular orbital theory is usually determined computationally, meaning this order, the middle thing, you have to use a computer program to figure out the order of orbitals. Okay? There is no single order that works for all molecules. The energy ordering for diatomic boron, carbon, and nitrogen is different from oxygen, fluorine, and neon. Most of the questions, if they ever ask you about molecular orbital theory, is going to ask, hey, why are these three different from those three? And here's the difference. This is the same. 2s give you sigma 2s and sigma stars 2s. So bonding, antibonding, that's the same. It's here there's the difference, okay? 2p orbitals, 2p orbitals, the way they interact will form 2 pi type 2p orbitals. So you go pi, sigma, pi star, sigma star. You don't have to memorize it. You just have to see the differences, okay? In this one, you get a sigma, pi, pi, sigma, okay? So going back to this is a pi kind of interaction, parallel interaction. This is head-on interaction. That's a sigma interaction, okay? So when the two p orbitals of boron, carbon, and nitrogen interact, you get two of the orbitals interacting parallelly, and they're actually lower in energy than the head-on one. Okay? In these three, you get one that's head-on, just like this one, but in this one, that one is lower in energy, and the parallel one is higher in energy. Okay? That's the difference in order. Question.
So if the only way to find this order is computationally, how would we know that on the left pi one starts and on the right the sigma?
You run the computer program and then it spits out this, and now you have to interpret it basically. You guys don't have to like look at a molecule and be like, oh, this is the order. You never have to do that. This will be given to you. You just have to explain why is it like that. How come in this one the parallel interaction is lower in energy than the head-on interaction? Okay, this is head-on. In this one, the head-on interaction is lower in energy than the parallel interaction. Both of these are parallel. Okay, so why does that difference exist? Basically, that's what you have to explain. Okay, it's a very
Explain that difference.
Yeah, why does it?
Yeah.
what is it?
Can you just explain like
Like,
why
how do we
is it
explain?
I'm going to explain why how you explain it.
Oh,
It's in the
okay.
next slide. I
Oh.
can't. Yeah, I need this picture for this. Okay. All right. The reason that the ordering is different is because there's something called SP mixing. Okay. You do not have to describe it to this detail. Okay. You just have to say in boron, carbon, and nitrogen, or boron, carbon, and nitrogen is different from oxygen, fluorine, and neon because of SP mixing. And here's what SP mixing is, okay? Let me see what this is. Okay, then you have 2s. Okay, so this is the diagram for oxygen, fluorine, and neon, okay? This is what it's supposed to look like. The head-on interaction is supposed to be lower in energy than the parallel interaction. This is default, okay? This is what it's supposed to look like. Oh, default. This is what it's supposed to look like. But these look different. So here's what's happening in boron, carbon, and nitrogen, okay? So this is the default. I know it's confusing, people's. I know. This is the default. See how it goes? Sigma, pi, pi, sigma, antibody. Okay? You're supposed to have the head-on interaction be lower in energy than this, okay? But here's what happens. This is called sp mixing in boron diatomic, carbon diatomic, and what is it, nitrogen diatomic. One of the p orbitals will actually mix kind of with one of the s orbitals. It's called sp mixing. They are close enough in energy that their probability densities, or the electrons in those probability densities, will interact. And when that happens, the one that's supposed to interact face to face gets pushed higher, and the 2s orbital actually results in getting lower energy. So think of it as orbitals don't exist by themselves, right? Think of it as electrons. When the electrons in S and P kind of interfere with each other, some of those electrons will give some of their energy to the electrons present in P, making those electrons have higher energy and therefore making the orbital have higher energy. And because the electrons in 2s lost some of its energy, they will go further down. They become more stable. These electrons get pushed further up. Okay, energy has to come from somewhere, right? So electrons are basically like interfering with each other, and the s electrons give some of their energy to p electrons. P electrons get more energy and go higher, and the electrons that lost energy go lower. So that's sp mixing. Okay, question.
And this happens because the S and P orbitals like originally had similar energy levels.
Yeah, they're closer together and they have similar energy.
So
yeah.
in like location wise, they're near each other because they have similar energy levels.
Yeah. Because boron, carbon, nitrogen's orbitals are more compact than oxygen, fluorine, and neon. Okay.
Oh, so that's why it happens specifically in boron.
Yeah. Okay. Now, the second thing that also gets pushed up is this. It's basically the same thing. Okay. So in these are molecular orbitals, by the way. Okay. These are not atomic orbitals. So the bonding or the electrons present in the bonding orbitals of this and the bonding orbital of p mix. These get pushed up, these get pushed down, and the electrons present in the antibonding, this is the second sp mixing, they interact the same way with electrons here. They will interact, and these electrons will get pushed up and these electrons will get pushed down. Okay, if there are electrons. Sometimes there are no electrons here, but if you put electrons there, they will be higher in energy. Some of the molecules don't have electrons in there. Okay, not all of them do. But in the ones that do have them, this probability density is higher in energy than this one. Okay, or where it was before. So here's how you would phrase an answer. In diatomic boron, diatomic carbon, and diatomic nitrogen, due to sp mixing, okay, the electrons in the molecular orbital that is formed from the 2s orbital will be lower in energy, and the electrons in the molecular orbital that is formed from one of the two p orbitals will be higher in energy. Okay? The electrons in the two p orbitals that are higher in energy are higher than, this is going to not be a concise explanation. The electrons in the 2p orbital that is interacting in a head-to-head direction will be higher in energy than electrons in 2p orbitals that are interacting parallelly. Yeah, that should be the second sentence. Okay, so due to sp mixing, the electrons in the bonding orbital of the molecule are lowered in energy, and electrons in the head-to-head p orbital will be pushed higher in energy, higher than the ones that are interacting parallelly. There, that should be a pretty good enough explanation, although I don't think it will be a FRQ question. I think it will be a multiple choice. So just read the answer and then pick the one that describes what I just said. Questions?
You're recording this lecture, right?
Yes, but I hope the mic is good enough to catch everything I'm saying.
Okay. If audio quality is good, you request it.
Yeah, but it's going to be kind of a choppy lecture because I'm talking, answering, but you guys can fast forward, okay? Just for people that are not here. Okay, so here is what you really need to see the differences. Like what you really need to interpret is basically this information and this information, okay? This is just the middle molecular orbitals. We're not showing any atomic orbitals here. We're showing the order of the middle ones, okay? So boron, carbon, nitrogen, these blue ones are the same for both. It's the red ones that are different, right? So the side-to-side interaction ones are lower in energy than the head-on interaction. But in boron, there are no electrons in any of these. You only have these, okay? It's only when you get to nitrogen that you have electrons here. Now, look at the bond order. You can have diatomic boron because it has a bond order of 1. You can have diatomic carbon because it has a bond order of 2. Everything's positive, okay? The only diatomic one you can't have is diatomic neon. Not possible because the bond order is 0. Now, bond energy. In diatomic boron, you have a bond energy that's lower than diatomic nitrogen. Remember, nitrogen has a triple bond when you draw its Lewis structure. So what we know from Lewis theory matches the bond energy calculated from molecular orbitals as well. Question.
Yeah, for the bond order, is that only calculated from like the highest energy level? So it's like the 2p level?
Bond energy? No.
The bond order.
Oh, the bond order? No, it's all of the electrons in bonding orbitals minus all of the electrons in the antibonding orbitals. So you would add 1, 2, 3, 4 minus 2 divided by 2 gives you 1. Yeah? You have to add everything in bonding minus everything in antibonding. Okay? So what we find from Lewis theory and all our other bonding theories matches what we find from molecular orbital theory as well. Okay? These have the shortest bonds. So here's what you have to interpret. Higher the bond order, more stable the bond, requires more energy to break, and shorter the bond. Okay? So higher bond orders indicate higher energy for bond enthalpy and shorter bond lengths, which matches valence bond theory and Lewis theory. Then over here, we know O2 exists. It has a bond order of 2. It's pretty stable. Intermediate energy compared to like nitrogen with a triple bond, right? Longer bond length compared to nitrogen, which is a shorter bond length with a triple bond. But look what happens when you distribute electrons into the molecular orbitals of oxygen. 2 go here, 2 go here, 2 go here, then 2 here, 2 here, then 1, 1. You have to fill based on Huns, right? So half filled and then pair them. But once you half fill them, there are no more electrons to fill, right? You're looking at 2 oxygens, so 6 valence electrons each, so 12 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What does that make oxygen do? What's the property of oxygen that cannot be explained by the other two theories that can be explained by what we just learned?
It's magnetic when
It's magnetic. It's
it's liquid.
magnetic when it's a gas too, except you can't like trap it and it's magnetic in all forms. Parallel spins cannot cancel out. So you have here and here, these magnetic fields can be canceled out. So oxygen is attracted to an external magnetic field. What else would be attracted to external magnetic field? Diatomic boron. Okay. So here is the gist of it. You have to be able to calculate bond order. You have to be able to explain why is these two lower in energy than that one because of sp mixing. These electrons in these three will actually be lower in energy than the 2s orbital here because this got pushed down and these got pushed up. Okay? Then You should be able to comment based on bond order. What would bond energy be and length of bond? Higher the bond order, higher the bond enthalpy, lower the bond length. Okay? And you should be able to tell me, based on a diagram, whether the molecule can exist or not. Okay? Now, liquid oxygen. Yeah.
Are you the given one where it's like we have two things with the same bond order and we're told to find which one has the higher energy or length?
Something with the same bond order, it wouldn't be that detailed. I'm telling you, it's just going to be like this picture with a multiple choice question. Yeah.
You would use bond order to see if it could exist or not.
Yes, you can use bond order to see if it exists or not. Yeah. Anything positive is going to give you existence. Liquid oxygen. There's a cool video. Anyone know what the color of liquid oxygen is? Anyone know what color oxygen is? What color is it? It's light blue. Isn't that cool? Light, light blue. There's two videos. One of them, yeah, they're both short. We can watch both of them. Here. The Grammarly dude is so annoying, honestly.
It used to be a different one. Rather than one. You see like the
Go away, Grammarly dude.
I know.
There's something wrong with the internet too today. So this is liquid nitrogen that he's pouring. So he's going to cool oxygen using liquid nitrogen.
Sorry, Daniel.
Just Daniel.
Look
So
over
I'm
to
going to take this oxygen gas,
I
pass
think
it
he's from
through
Harvard.
this copper coil that's
Maybe
immersed
people
in
in
liquid
Harvard just
nitrogen.
know Daniel.
Liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled door. We will then take the liquid nitrogen and pour it between the poles of this
Look at that
magnet.
giant magnet.
We'll pass the oxygen also, pour it through the poles of the magnet, and then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
In here is liquid nitrogen. It's evaporating too. But that's just water vapor. Right? It's like fog.
It's weird to think that things can boil at room temperature.
Yeah. Good thing we don't. Oh, the coil is it's hollow. He's passing the oxygen through it, and then it's cooling as it goes through, and then
It's like condensed.
coming in there. Yeah. Look at that.
Actually, a lot. Wow.
This is called a condensing column. Isn't that pretty? It's like light blue.
That looks like a last.
If you set fire to it, it would be very dangerous. Look at that color. So he's passing liquid nitrogen through the magnet. See, it's not like getting suspended. He's also cooling the magnet, so the oxygen doesn't just become a gas. It doesn't get suspended between the two magnetic poles. See, it'll actually stay there. So it's attracted to the magnet. But it's becoming a gas. It's because it like has to stay so cold. But yeah, that is very cool. But it's not water. Can you imagine there could be a planet where oxygen is liquid somewhere out there? That's so
Yeah,
cool.
give it cold.
Yes. What?
Yes, you
So we did a whole unit on thermal chem. What is gonna happen to the thermal energy in your body? You would just freeze on the inside. Yes. 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 You will literally. Okay, number one, all that liquid oxygen, if you drink it, it's going to expand inside your body because becoming a gas, you would probably, it will come out in a big cloud of oxygen gas, damaging you, and this would be completely frozen. Okay, touching quickly. I don't know about the oxygen, but you can definitely touch nitrogen quickly. Not instantly. It wouldn't be instant.
If you move it around constantly, it doesn't like
It wouldn't be instant. Like liquid nitrogen, you can put your hand in because the liquid nitrogen becomes a gas as it touches your skin. You're protected for a little bit of time. If you keep it submerged, it's no good. You can put hand. So I'm guessing it's the same for oxygen.
theoretically, if you
We can get some liquid nitrogen at the end of the year.
so before like your jaw completely froze, if you were to put liquid oxygen in your mouth, right, let it evaporate for a few seconds, hold a match right here, and then like breathe out, could you technically breathe fire for a short period of time before you die?
Yes, but sure, but you will die.
Yes,
I mean,
I'm
also,
aware.
some of that oxygen is not just going to go out. You might have, and it might end up in your throat. It's just going to explode. You might just not even have a face by the end of it.
No, I'm aware of the fact that you would die. I'm just saying, for a short period of time, and by that I mean like half a second.
A short period of time,
For like
you
a
would be
second.
very cool, but also literally very cool, but also very dumb. So yeah.
Well, yeah, they just use okay.
Okay, so peoples, real quick, couple of slides to look at. Okay. Look over here. Now that you have a basic understanding of molecular orbital diagrams, let's look at some very simple things that you have. Hello. Simple things that you have encountered. Okay, so NO molecule. So far we've only done the same atoms, but diatomic. This is atomic molecules. So far, we've been looking at homonuclear, meaning the two atoms that made the diatomic molecule was the same, but in this one, it's a different um, uh, grouping, or I mean, different atoms are bonding together to just form a diatomic molecule. Nothing more than diatomic in this diagram. Okay, so you have the nitrogen monoxide molecule here, and you can see that you have the nitrogen atom here and the oxygen atom here, and the nitrogen atom's 2s orbital is slightly higher in energy and the oxygen atom's 2s orbital is slightly lower in energy. Okay, now the oxygen atom's 2s orbital is held closer to the nucleus because oxygen has a higher nuclear charge. Remember, that was a question in the 6+8 test. Okay, so because of that, oxygen's 2s being closer to the nucleus is lower in energy. Okay, because oxygen has a higher nuclear charge. Now look at the way that the molecular orbitals are formed. So the molecular orbitals are the ones in the center, right? So look at the way that the molecular orbitals are formed. I'm going to get a pen because I'm not sure you can see the cursor. Okay, so these are the molecular orbitals. Okay, so when you have two different atoms and their atomic orbitals combine to form molecular orbitals, the orbitals have more of one or the other's character. What I mean by that is, it's right here. Orbitals are lower in energy in more electronegative atoms generally, also because the 2s orbital is close to the nucleus. And the lower energy atomic orbital will have a greater contribution to the bonding molecular orbital. So this one is the bonding molecular orbital, right? That's the bonding one. And that one will have more of the oxygen's 2s character than nitrogen's 2s character. Okay, so that means, let's say the oxygen is like blue and then nitrogen is yellow. When blue and yellow mix, we know that it makes green, right? So this orbital would be a bluish green, and then the anti-bonding orbital would be like a yellowish green. Okay, so if you have blue and you have yellow, oxygen being blue, there be more oxygen's 2s character in the bonding orbital than nitrogen's 2s character. Okay, so lower energy atomic orbital will have a greater contribution to the bonding molecular orbital. It'll be closer in energy than the antibonding. The higher energy atomic orbital will make a greater contribution to the antibonding orbital. So nitrogen's 2s will contribute more to the probability density and the energy of the antibonding orbital. Okay, so that's what I wanted you to see. Um, and this is a free radical. This is one of those molecules that have a single unpaired electron, and it's in a pi star antibonding orbital. This is called a free radical. Okay, and then this is interesting because this is HF, huge electronegativity difference, right? We know that around fluorine there are 3 lone pairs like that. And this is how the bond forms with hydrogen. It's not actually fluorine's it's not actually hydrogen's it's not actually fluorine's 2s that bonds with hydrogen's 1s. It's actually fluorine's 2p, because fluorine being so electronegative, the energy of the 2s orbital is so low that it cannot actually interact with hydrogen's 1s orbital. Hydrogen's 1s orbital is all the way up here, and fluorine's 2s orbital is all the way down here. The two the 2s orbital of fluorine cannot bond. It's too far apart in energy to interact with the hydrogen's 1s. Okay, so this is actually one of the lone pairs in fluorine. This one is a lone pair orbital. Okay, and then over here you have one of the 2p's. You don't really have to know how these form, right? This is where one of fluorine's p orbitals and hydrogen's 1s, they will combine to form the sigma bonding, and these will be basically the other 2 lone pairs in fluorine. So these are the 2 lone pair orbitals. These are the p orbitals that are right here. They're non-bonding orbitals. Okay, non-bonding meaning they don't actually form any molecular orbitals. They're just non-bonding orbitals. They hold lone pairs. This is a bonding orbital, and this one is an antibonding orbital. There are no electrons in the antibonding orbital. This is the bond. This one is that. I'm just trying to expand your understanding of how bonding happens here, okay? So here is something that you actually need to definitely know to answer questions. Just interpreting like the picture, that's all kind of what you need. This is the Lewis structure version of ozone. That's the basic one. And then you have valence bond theory version, where you either have to have the pi bond on these 2 oxygens, or that has to break and the pi bond has to move to these 2 oxygens. So it's just same as the resonance present in Lewis structures, okay? But we know for a fact that it's a hybrid of these 2 molecules that exist, not this one or that one. So the fact that it's a hybrid is explained by the molecular orbitals of all 3 oxygens. These are the bonding ones. This is where you would have all of the p's, the parallel p's will interact with each other to form bonding orbitals, and you have a resonance hybrid. Okay, not to say like this one doesn't happen. Okay, this one does happen sometimes. That will this areas interactions will get interrupted and ozone will look like that, but not all the time. It'll be very 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 rare. Okay, and you don't have to necessarily like understand this one. This is just representing the 2 lone pairs of each oxygen. These are the ones that are not you know participating in bonding. But yeah, you don't have to understand the non-bonding one. Don't pay attention to that. You should just pay attention to that. You can see how the molecular orbital stretches across all 3 oxygens, forming that resonance hybrid, okay? You don't even have to really interpret that. Okay, then the next one is just a bunch of other molecules. This is benzene. So this is benzene. We know benzene, we write it like this. Benzene has double, single in bonds that interchange, but it's not exactly like that. It's actually like that. It's a resonance hybrid of all of those bonds, and this is the molecular orbital that allows that to happen. Basically, all the unhybridized p's in each of these, they will all overlap to form like this nice circle. I'm not using my pen, I'm using the mouse, which is why it's all skewed. But all these unhybridized p orbitals will basically like merge together to form this big balloon structure up above and below, right? And then you'll have this spreading of all the p electrons in the entire circle. This is called delocalization. The pi electrons don't belong to any individual carbon, they belong to all 6 carbons. Okay, so you end up with this electrostatic potential map where you see a big ring of electrons in the middle and then all of the carbons at the edges, okay, and the hydrogens. So this is a molecular orbital. That's a molecular bonding orbital in benzene. And that's it.